recording now. So what we'll do in the next 1.5 hours, or what I'll do, is give you really a very basic introduction to the key concepts of information theory, and that's mainly, say, located in the Shannon information theory part of the entire domain. There's a whole lot more about that, but which we will maybe cover at the workshop to some degree. And that will take about 1.5 hours. And at the moment, we devoted 2 hours for this meeting, so I hope there will be a lot of interaction and questions. Also, please always interrupt me while I'm talking, so we get the most out of this meeting. And whatever we cannot solve today, we'll solve at the workshop then. So I know a lot of you already have a background in information theory, so some of these concepts may sound very familiar to you. And if they sound familiar to all of you, then we can just, skip something and move on. Okay, to get you pulled into the topic, I have created a survey. Can you see that now? It's actually the first survey ever I do with Zoom. And it's a very simple question I'm asking to all of you. How many people do you think live in Karlsruhe? And Martin has a head start on that because he lived here once. So please just do one vote, and I gave you, say, a set of classes. Okay, I think now everybody except Gray has replied. So what we now have, where do we see the results now? Can you see the results? Okay, so
yes.
What we have now is a very nice, say, probability distribution, which is the summary of the guesses of all of us, except me, about how many people actually live in Karlsruhe. Yeah? And this we could see as a formalized way of communicating our best guess about how many people live in Karlsruhe. Okay? Now, I'll tell you, there are 308,000 people living in Karlsruhe. Okay, and now try and track what happened in your mind when I gave you this this piece of information or this piece of data, actually. Before, let's say, we all had this probability distribution in mind. That was the result of our survey. And this then basically collapsed to a single number, if you trust me, that is, the crisp value of 308,000. So what really happened between these two states of your mind was you received some data, and the data realized that you changed your probabilistic state of the number of people living in Karlsruhe from uncertain to a crisp number. Now, I'll do something else. I'll tell you, there are 308,000 people living in Karlsruhe. And you may have just realized I told you the same thing again, yeah? And it's exactly the same piece of data that I passed to you, just twice. Now, the second time, you were probably not very surprised anymore. And your probabilistic state of mind about how many people live in Karlsruhe did not change anymore. So the key thing I want to convey here is you received exactly the same piece of data or the exact same signal, but the information content for you was completely different these two times because your prior state of uncertainty was different. So the key thing, I'm now starting the presentation. Can you see the PowerPoint? Okay, so one key aspect about information theory is that data is not the same as information, okay? So data are carriers of information, and the data carriers can be completely different, but they're not the same as information. Now, let's do a second example before we go back to the introduction. let's say we play dice. Yeah, for simplicity, we use a 4-sided dice, which can show 4 numbers, 1, 2, 3, 4. And as you can see here, because you rolled the dice for a long time, you can see these 4 distinguishable outcomes come with equal probability of 1/4. And now imagine we're playing a game. I'm rolling the dice here on my table, hidden, and I'm asking you to guess the outcome of this particular roll of the dice, okay? And you can try and find out by asking questions to me that can only be answered by yes, no. So you ask binary questions. And the goal is here to identify the outcome with the least amount of questions possible, okay? So let's formalize that a little bit. This is where you start from. Yeah, that's your prior state of uncertainty. You know, there's a 25% chance for each of these numbers to pop up. And now I'm rolling the dice and I see the number, but you don't. Which question would you ask me?
We can either ask if it's an odd or an even number.
Yes, that would be a good question, actually an optimal question. How come? So how did you come up with this question?
It was just one question that splits the set of possible solutions to 2. The other question I had in mind was, is the number above or equal to 2? Or above or equal to 3, or below or equal to 2?
Okay, so you're very close to say the perfect strategy for asking questions, but not quite. So your question was perfect, but your reasoning was not perfect yet. Does anyone else have a justification for this question? Is it even or odd?
I'm not sure I know how to explain it exactly right, but somehow the total space can be expressed in 2 bits and the even or odd question gets one of them.
Yeah, that's also very close. So the solution is an optimal question always splits the probability space into 2 equal-sized halves. So it's not the number of states. Say here we are lucky because the states are uniformly distributed, but an optimal question is one where half of the possibilities, half of the probability vanishes by the answer that you receive. So asking, is it even or odd, is perfect. You could also ask, is it smaller than 2.5 or not? Yeah, that would work equally well. Now let's say, let's say I rolled the dice. No, I'm not telling. Let's say I said it's even. Yeah, that was the answer. What would be your next question? Daniel, are you trying to say something?
I didn't, but I can. Is it 2?
Yeah. Yeah. So now you have 2 possible states that are left, and both have a 50% chance. So you can ask, is it a 2 or is it a 4? Doesn't matter. Yeah. You will identify then by the yes or no. So if we repeat this game many, many times, yeah, such that the 1, the 2, the 3, and the 4 all pop up eventually, this will be the question tree or the decision tree that will then emerge from your optimal questions. Yeah, and you will always start here and go down this tree until you have identified the correct result. And you can see here how the probability space here, there are still these 4 events or outcomes included, will slowly become smaller until there's only 1 outcome left. So we can now start counting the number of questions that we need. Actually, each question here is 1 branch of the question tree. So for each of these outcomes here, we needed to ask 2 questions and 2 optimal questions. That's important. Yeah, this tree is a tree that was built on an optimal question scheme, the one that splits probability space in half. And the probability with which we arrived at each of these trees simply is, the long repetition result of these outcomes. So the probability, the relative frequency, 25%. And now comes the interesting part. If you take the negative log to base 2 of the number of questions that we asked for each of these branches, if you take the negative log of the probability of each of these outcomes to the base 2. Base 2 you need because you asked binary questions that only allow for a yes/no outcome. Then you will see that this negative logarithm exactly equals the number of questions. And information is defined as such as the negative logarithm to a chosen base of the probability of a certain event. So it has this direct interpretation, information, as numbers of questions that you needed to ask until you arrive from a given prior state at a given posterior state. And if you would be allowed, for example, to ask not binary questions that I can only answer with yes, no, but where I'm allowed to give 10 possible answers, then the same thing would apply, but it would be the log to base 10. Yeah, then it would not be called bit. The unit of information is bit if it's on base 2. And that's actually the most standard one because our computers all work with binary states. So they do information processing on binary states. And also it's easier to ask questions where only 2 outcomes are possible. So this is what makes the concept of information very attractive to me because it has this very intuitive interpretation of optimal questions you need to ask, or vice versa. If you received some information, it meant you were spared having to ask a certain number of binary questions. Okay. Now, after this introduction, I'll go quickly back to show you what's on the menu for today. So we will look at the very basics of information theory, information entropy, and key terms like conditional entropy, joint entropy, mutual information. We will talk a little bit about limits, so upper and lower bounds of information. Then, because it's quite an important concept in causality analysis, we'll talk a little bit about the concepts of independence, redundancy, and synergy in data. And also because it's important for modeling, especially for dynamical time series modeling, we'll talk a little bit about conservation, dissipation, and innovation. And this is also where some connection shines up with the thermodynamic interpretation of entropy. And then I'll very quickly show you some applications and point you to some further reading. And again, please always stop me and ask if you think that something needs to be specified and clarified. So basically, this equation here, information or definition of information being the negative log of the probability of an event, is more or less the Big Bang of information theory. And it was released by this guy, by Claude Shannon in 1948. In a paper where he was basically thinking about how to efficiently and at a certain level of security transmit signals through noisy channels. And then later it showed that this concept of information entropy that he came up with, carries much wider and broader than he initially thought.
Can I make a comment?
Sure, yes.
Just because I ran across this recently, I thought it was interesting to make the connection to machine learning. That when you're doing a classification problem and you're ultimately trying to classify images as dogs or cats, that you're essentially reducing it to one bit of information, one question at the end. The decoder has to answer the question: is it a dog or a cat?
Cat, yes, no, basically. Mm-hmm. Okay.
So even if the data contains a lot more than one bit of information, you have to pick out that specific one bit of information, which allows you to successfully choose between one. Sorry, that's what I meant to say.
Mm-hmm. Okay, and so this interpretation of information as the number of binary questions holds not only, say, if you start from a probability distribution and end up at a crisp result, it also holds for any move within that tree, so any subtree. You know, if this would be your prior state, if you would enter the guessing game where people already have identified it's a 1 or a 2, and there's just one further question asked, then you would have received 1 bit of information. So it holds for any subpath in a questioning tree. Okay. And if we say information is the number of questions we were spared to ask because someone gave us some fact, me telling you what the number on the dice is, you can simply flip this expression by saying uncertainty is then the missing information, the information you still need to gather by asking until you have reached a certain state of knowledge about some fact you're interested in. Yep. So it's just going up or down the question tree, basically. And so here with information, we also have a nice interpretation and definition of uncertainty. But also you have to keep in mind what we need to calculate information is proper probabilities. So you either have to have, you know, already a good idea of what the probability distribution is, so you can give a probability to a particular event. If you have only very few data and your probability distribution is still uncertain, then you pay with added uncertainty because you don't even know exactly the probability distribution. This too can be, say, formalized and measured with information concepts, which I like. That means that you can also, in the same language and with the same currency, express uncertainty due to data variability and uncertainty because you don't know exactly how the data are distributed. And this is, we will see that later. This is measured by cross entropy and Kullback-Leibler divergence. And this is where uncertainty due to using a model of some data relations and not the real thing comes into play. But you can measure both of these aspects, uncertainty due to variability of the data themselves, of the data generating system, and our lack of full knowledge of it can both be quantified in the same terms. Now, here's another interesting fact that points to, say, a large chapter in information theory, and that would be encoding and compression and encryption. So I'll very briefly touch this topic only. Let's say we would label our question tree here that we built, our optimal question tree for guessing data coming from that system. Each yes branch, say, or always the left branch here with a 1 and the right branch with a 0. Then you can immediately see that every path that we go down here has a unique sequence of 1s and 0s. Yeah, so identifying a 1 would be a 1-1 branch sequence. Identifying a 2 would be a 1-0 branch sequence, and so on. Yeah, and this would hold for any number of distinguishable states that our probability distribution has. And what I want to point out with this is basically we can now express any set of symbols from an alphabet. Here it would be the 1, 2, 3, and 4, but it could also be an A, B, C, and D with a binary sequence of signals or letters. Yeah. So that's just a short hint that with only 2 distinguishable states, but enough of them, we can represent any alphabet that we want. And that's actually what our computers are doing all the time. So there's no no lack of generality if we now work with binary data and only two distinguishable states. Yeah, every computer scientist, I guess, knows about this. So, for example, whatever H2O would be in a binary encoding would be simply this sequence here. And this goes way down a rabbit hole here, this idea, but we're not following it right now. Okay, here's some useful properties of information. You know, due to the nature of the logarithm, and because we know the probabilities of an individual signal or outcome of a probability distribution can at the smallest be a 0 and at the largest be a 1. The log transform of these values then goes between 0. So information can at the smallest be 0. So there's 0 information in a certain event. Yeah, if an event has the probability of 1, you know already this and only this will happen. Its information content will be 0. Now, the more rare an event becomes, the smaller its occurrence probability, the higher the attached information. And basically, the almost impossible event will carry almost infinite information. That means there's another interpretation of information, and that is the concept of surprise. The more surprised you are, the higher the information content of the signal you just received. And that means also that if you would, you know, in German language at least, the vowels are pretty frequent, the A, the O, the E, and so on. So if I would continue talking, leaving simply away the vowels, you would probably be able to decode what I'm saying, to translate it, because the vowels, they don't carry much information. Yeah, you can usually identify a word, even if the vowels are taken out, because it's actually the rare other letters that allow you to identify which word is currently meant. And so this is one thing that's good to keep in mind about information. It's log relation to probabilities. And also that's a useful mathematical property, say, because we do log transforms of probabilities. The combination of independent probabilities, say you roll 2 dice and you want to calculate the joint probability, that's the product of the two probabilities. Yeah. So the chances to roll a 1 and a 1, if you roll 2 dice, is 1/6 times 1/6. So it's a multiplicative combination of independent events. In the log transform, this becomes addition. So the information then attached to these two events would be log 2 of 1/6 plus 1/2 of log 6. And that also means you maybe know that from Bayesian, from maximum likelihood calculations, where you have to calculate long sequences of products, which then entail the problem of diminishing or vanishing products. Often you cure this by taking the log likelihood, and that's actually nothing else than information. Yeah, because of the log transform, you convert the necessity of multiplication to simply addition, which is much more stable. Now, so far we talked about information attached to individual events. Yeah, me rolling the dice once, and the information attached to the outcome. If we do that guessing game for a long time, so rolling the dice many times and calculating how much information on average did you receive by these 100,000 signals that we produced, then this is entropy, nothing else. Yeah? Entropy, information entropy, is nothing but the expected value of information. So that means it's simply the probability weighted information attached to each signal. So if a certain signal has a probability of popping up of 0.25, and the information attached to that is 2, yeah, you simply take the probability weighted sum over all these signals, and that's entropy. So entropy is a property of this entire data generating system or the entire probability distribution, and not of an individual signal coming from that distribution. So if you're a statistician, you could also say entropy is a measure of spread of a distribution, much like variance would be. The difference is that variance comes in the units of the data that you're looking at, and it's mostly influenced by those values that are far away from the mean. Entropy always comes in bit, so it's independent of the units of the data, which makes it easier then to compare distributions of different units. And it's mostly influenced by the high probability outcomes. Okay.
I mean, I guess it's obvious, but here the log is just missing, no?
No, because information here
I see
already
you have
contains
it in
the log.
here. Yeah, okay. Yeah.
But is then divide by n missing to get like the average?
That would be the case if you
can do
simply
both.
add up the informations, but as you multiply it with their occurrence probabilities, and these sum up to 1, you don't need to divide by n anymore. So it's already normalized to 1.
Okay, so this is for, sorry, I maybe missed this, but this is to get the expected for like over all possible samples. I thought that
Over
you
all
said before,
outcomes.
over all outcomes and not over all samples, because I thought I heard that you said if you, for example, throw that 100 times, and I thought it was related to the n equals 100 and not to the possible outcome, but then I missed this.
So you could do it that way too. If we roll the dice 100 times, you keep the information that was attached to each outcome, and then you simply take the average of these 100s. You arrive at entropy, or you summarize these outcomes. You group them into the same outcomes, and you simply then calculate the probability of each outcome, which is a summary of its relative occurrence frequency in your 100 signal string, and then you can calculate it that way.
Although I think that these two pictures are only equivalent if your dice throws are independent of each other, right? Otherwise, it doesn't necessarily need to end up at the same value, I guess.
Yeah. No, actually not. If your probabilities, if your sequence of dice rolls is long enough to get a robust representation of your true probability distribution of outcomes, this will yield exactly the same result.
But it's true that if you have conditional events, then you would be measuring the conditional entropy. So.
Okay, then things are getting more interesting. You're right.
Yeah. But I think here you assume you have knowledge about the true probability distribution. So no matter what, you would infer it.
So for the cases where, say, sequences of outcomes are of interest because they're somehow correlated, you would have a larger probability distribution over these combined events. And then entropy calculation would hold again, but it would be a larger probability distribution because the set of distinguishable outcomes would simply be larger. I see you already think in causality terms and dependency structures. Okay, so entropy simply is expected value, or flatly put, the average information. Yeah, Hoshin?
Just to clarify one point which might have gotten confusing. It's true that you're measuring entropy in bits, but it does depend on the scale of x. So if you were to double x the probability distribution would become flatter and wider. If you were to change from x to 10x or x by 10 or whatever. So the measure of entropy does depend on the units in which you measure x. It's not independent of the units, even though it still appears in bits. And
No.
of course, it also depends on the bits.
No, I disagree.
Yeah.
If we draw on our dice not 1, 2, 3, 4, but 10, 20, 30, 40, the information attached to any of these signals would still be 2-bit, and the entropy of that distribution would still be 2-bit.
Okay, sorry, I'm confusing continuous and discrete entropy.
Mm-hmm.
In continuous entropy, it does depend on the scheme.
That's why continuous entropy is such a challenging thing, and that's why I like to stay in the discrete domain. So all the examples that I show are now in the with discrete samples, but there are equivalent expressions for continuous data. Okay, so to get a better idea and a grip on entropy, let's take a look at these 3 distributions. Yeah, it's always systems that produce 4 possible outcomes, but the probability distributions over the outcomes are different. So system A here, all outcomes are equally probable. System B only produces 3s, and system C has some, that's a biased dice that has been used for a while, or the dog has chewed on it. So it provides some bias distribution. Now, what do you think, which produces the highest and which has the lowest entropy of these distributions?
A would have the highest entropy.
Absolutely. If you have to guess outcomes coming from system A, you have to ask the highest number of questions, yeah? Because you're most uncertain before. And the lowest then obviously is system B, because if you know the distribution, you already know beforehand, you can say, well, the outcome will be 3. Yeah. So oops, that was the wrong direction. The entropy of this distribution is 0-bit. You need to ask on average 0 questions. The entropy of this distribution is 2-bit. And the entropy of this distribution is 1.75-bit, which is somewhere in the middle, yeah, intermediate between these 2 extremes. And these are actually the extremes. A Dirac distribution always has 0 entropy, which is a lower bound. And the uniform distribution over a distribution with a known number of distinguishable states always has the highest of all possible entropies, which is simply log 2 over the number of distinguishable states. So that's a nice property about entropy, that you have an upper and a lower bound, yeah, which is maybe not the case if you work with variance. And one thing I'd like to mention here also, if you have such crooked distributions, of course, your question tree will look different from this one here. And sometimes it will not be possible to ask an optimal question, because you cannot come up with a question that will split the probability space exactly in 2 halves. So if that's the case, at least there is an upper bound to the additional number of questions that you will need to ask, because you cannot ask optimally, and that will be 1-bit. Yeah, that's also somewhere the proof is in Cover and Thomas. So that means you don't pay infinitely if you cannot ask optimal question, but there is a relatively low upper bound to that. So just as an example, here the first question with this distribution, if you want to split the probability space in 2 halves, would be, for example, is it a 3? Yeah, because 3 has a probability of 0.5. And then you will either, if it's a 3, arrive at the answer already, or you're left with these 3 states and then you ask on. Okay, so that means if we know that rare signals are highly informative, then we can also ask the question, how much information can we transmit with different alphabets? You know, we do have 26 letter alphabets in France, in Germany, and in the English-speaking countries. The Chinese have many more, like 9,000 or so letters. And what you see here is simply the probability distribution of the different letters in our alphabets, in like if you take a dictionary or a newspaper and just count letters. Yeah, so you can see here in German, we hardly ever use the Q, but we very, very often use the E. And the French also use the E, but more often the Q, and so on. Okay, and the Chinese,
they
have...
Chinese ones are ranked.
Sorry?
I assume the Chinese ones are ranked, whereas the other ones aren't.
Yeah, exactly. And now if we calculate the entropy of these distributions, that gives us a hint on how much information we can convey on average with any single letter that we pass in that language. And you can see the entropy of the French use of our alphabet is 3.9 bit, ours is 4 bit, English is 4.2 bit. So comparing these, you can see the English make most efficient use of their 26 letters, meaning their use of the letters resembles a little more a uniform distribution, yes, than in the German or French. But then we are all outsmarted by the Chinese use of their letters. Here the entropy is 9.6 bit, meaning that on average, with any letter that is passed in a Chinese, say, phone call, you pass on 9.6 bit of information. So the obvious question then is, why don't we all switch to a Chinese alphabet? We just have to learn, 9,000 letters once, but then each of these letters is so much more informative than any of our 26 letters. Actually, we should, if we hadn't invented something smart that highly increases the information content of the letters that we pass on. Do you know what this smart move is?
Words?
Exactly. We combine, we don't, communicate in individual letters of the alphabet, but in combinations, and that's words. And the joint information of a word is then simply, the sum of the entropies. Or sorry, by creating words, we're creating a much larger alphabet, basically, because each word has a meaning and not each letter. And then our use of language becomes as informative as the Chinese use. Yeah, we still have less words than maybe the Chinese symbols, but we arrive at the same information content that we can pass on. And this leads to things like Huffman encoding and the question, if any of you knows the Morse alphabet, the question would be, which of the letters should get the shortest signal? And that would be, of course, the most frequent. Yeah. So, in the Morse alphabet, the E is simply a dot. So that's the shortest signal you can think of. Because it appears most often, it gets the shortest set of symbols to pass on, and so on. So this is another fascinating and interesting domain of information theory about communication and how to do that most efficiently. Okay, so now we have two key concepts, information and entropy. And so far we were only looking at univariate distributions. What happens if our probability distributions are more than 1D? Yeah, if we have joint measurements of, say, rainfall and temperature or so, can we also calculate the entropy of this joint data set? And of course we can. Imagine this is the marginal distribution of rainfall. This is the marginal distribution of temperature. Yeah, and I'm distinguishing only 3 states here. Then of course, because we have joint measurements of or paired signals, we can simply also populate a joint distribution of these paired signals. And then we have a probability distribution that is two-dimensional, but still sums up to 1 and qualifies, as a probability distribution. So now we can calculate the entropy of this two-dimensional distribution as before. We simply add up the probability weighted information attached to any of these outcomes. Yeah, so now it's the log 2 of the probability of a joint particular outcome. Say rainfall was 10 and temperature was 1. And because in counting these probabilities, there is no need for keeping a certain order. You could cut, if you like, this two-dimensional distribution into pieces and make a long string out of it. It would not change the value of the entropy. That means calculating information measures in high-dimensional spaces is not more complicated than in a one-dimensional space. Yeah, and that's what makes a difference between this and value-based measures of spread, where the relative positioning of these outcomes plays a role. Okay, so, and this is called then joint entropy. And this can be interpreted then as the average number of questions you need to ask to guess a paired signal. In a dice rolling game, that would be, you're not guessing a single roll of a dice that I'm rolling, but I'm rolling 2 dice at the same time. And then it's maybe the outcome 3 and 6, and you have to guess the paired outcome. And the number of questions you need to ask there would be the joint entropy of this distribution. Okay, and now comes a shift. Now we're basically introducing something like a state before and a state after. That means what happens if we have prior knowledge of something before we are asked to guess some outcome. So far, our prior state of knowledge was knowing the shape of the distribution only, and we had to guess an outcome. But now someone could give you additional side information. And this would be a typical case, for example, let's say we have these joint measurements of rainfall and temperature again. And now I'm asking you, what is the temperature today if I already tell you the rainfall today is 5 millimeters? Yeah, so it's a question conditioned on some prior information, some side information that I gave you. It's like asking, what is the outcome of this roll of dice? But I already give you a hint, it's an odd number. Yeah, so that is side information that can be useful and can reduce your numbers of questions. What this essentially means here, if I give you the value of the rainfall being 10, you're not guessing from this distribution, but you're guessing from the conditional distribution of rainfall being 10. So this sub-distribution here, which is simply the conditional distribution, or if you look at it here in this joint distribution, because I'm telling you a value of y, you now have to ask only based on this conditional distribution. Now, if you're unlucky for a particular conditional distribution, this may have a higher entropy than the overall joint distribution. So you need to ask more questions. It could be that it's less questions, or it could be that it's the same number of questions. But the important thing is, on average, if you do the questioning game with side information many, many times, you will always have to ask no more than the question you would have to ask if I hadn't given you side information. That's in colloquial language, this means information can't hurt. Yeah. So side information never increases. If you're lucky, it decreases. And if it's completely independent of what you're interested in, it keeps the number of questions the same. And this is this number of questions, average number of questions you need to ask if you have site information, is called conditional entropy. So the entropy of what you're interested in X given a value of Y. And this, you can imagine, is simply the probability weighted conditional entropy of a particular distribution that you select because you have site information. So if I always give you Ys, the conditional distributions are these vertical distributions here. You can calculate the entropy of each, and you multiply these entropies, these conditional entropies, with how often they appear. How often they appear is simply stated by the marginal distribution of your conditioning variable, and that's conditional entropy. Does that make sense? Okay. Now, that's a key concept or a key theorem in information theory that's called the information inequality, that the conditional entropy of X given some predictor Y is always smaller or at worst equal than the unconditional entropy of your target distribution that you're interested in. Yeah, so that means information can't hurt. If you like, you can throw more and more predictors into a guessing game. They won't hurt. Except, and those who work with large data know that there's a catch, and that's the curse of dimensionality, meaning if you add more and more predictors, while they don't hurt directly due to the information inequality, it severely blows up the dimensionality of your problem. And that means the data set that you have quickly becomes pretty sparse to populate this high dimensional probability distribution. But that's not, say, the fault of the predictor. Okay, and now here's some graphical, say, displays of how these information measures are related to each other. Because information terms are additive, you can nicely depict that with something like Venn diagrams, where the size of a certain symbol here represents the amount of entropy or conditional entropy. So let's say we have two pieces of data, X and Y, and the unconditional entropy of each would be illustrated by a circle. Yeah, the size of the circle here, that's the entropy of X. And the size of the blue circle here is the entropy of Y. The entropy of the joint distribution, if we had paired observations of X and Y, would simply be the total area covered by both of them. If they would be completely independent of each other, then the pictorial correspondence would be these two circles are apart, and the joint entropy would simply be the sum of the two entropies. If, however, one set of data knows something about the other, in the sense of that it reduces the conditional entropy, you can depict that with an overlap of these two areas. And the overlap is called the mutual information. And what's left of the original unconditional entropy, so this, say, half moon, here would be the conditional entropy of X if you have knowledge of Y. And the relation between the three here, joint entropy, unconditional entropy, and conditional entropy, is simply that joint entropy, the size of the full circle, can be either the unconditional entropy of X plus the conditional entropy of Y given X, which would be this part, or vice versa, the unconditional entropy of Y plus the conditional entropy of X given Y. And this lentil-shaped area in between is the mutual information, which can be calculated as either the unconditional entropy of some variable minus the conditional entropy of that variable given the other, or vice versa. That also means that if you have two sets of paired data, each of them knows as much about the other than the other way around. Yeah, in causality, this may be hard to accept, that rainfall knows as much about discharge than discharge knows about rainfall. But in terms of the data strength of relation, it holds. But this area here in absolute terms, of course, has the same size for both. But in relative terms, it can be a smaller or lesser portion of the total unconditional entropy. That means mutual information is the same, but it's relatively more if you're asking about Y than if you're asking about X. Yeah, so that means in a relative sense, rainfall may know more about discharge than discharge about rainfall, but the mutual information among them is exactly the same. Okay, so far we've been always keeping this concept of uncertainty in the back, and we are always talking about distributions. And so I think it's time to think about what are sources of uncertainty anyways in what we're doing. And I've collected a few, maybe you know some more. The first would be one source of uncertainty that simply comes from the variability of our system, that our system can produce more than one distinguishable state. And because of influences that we have no hold on, this is basically a random process for us if we see a 1, a 2, a 3, a 4, a 5, or a 6. Yeah? So that would be a source of uncertainty that comes from system variability. If we had perfect knowledge of all the molecules of that dice and the environmental conditions, maybe this would be no source of uncertainty for us anymore, because we could perfectly predict the outcome. But on that practical level of we're rolling a dice, this is a source of uncertainty. Secondly, we could add uncertainty to our analysis because of limited sample size. And that's very often a key issue. Let's say we only observed 4 rolls of the dice, and from that we create our probability distribution of the possible outcomes of that dice. Yeah, then simply due to limited representativity of our data set, there will be predictive uncertainty about what the next roll of the dice will be. Yeah, and we will not ask optimal questions when we have to guess the outcome of a dice roll. Third case would be, and that's quite related to the second case, consistency, meaning if we learn in one system, let's say we have here a 6-sided dice, we roll it a trillion times, we get the perfect probability distribution of its outcomes, but then we apply what we learned to a 21-sided dice. Yeah, then clearly what we have learned is not really applicable to the new system, and we will pay with additional questions. And this then has, these are extreme cases, the way I'm showing them, but let's say in learning from collections of catchments and then applying what you've learned in an LSTM to a new catchment would be a case of consistency. Yeah, if they are not perfectly representative, these systems that you learned from, to the situation you apply what you learned to, you will add uncertainty. And the last case would be compression. Let's say you're limited in your resources, and that's always the case. That means even if you would have the perfect data sample to learn from, you only have, say, 1 bit of memory to store what you learned. So probably the best what you can do is to store your probability distribution of your dice at a single number, which would be the average value or expected value, a 3.5. That would mean every time you roll, I ask you, what's the outcome of this roll of dice? You would say 3.5, yeah, because that's the only thing you stored. And that means you will pay with additional uncertainty because you had to compress what you knew to a smaller set. This opens then again the gateway to lossy and lossless compression, meaning how can we express what we know with lesser bits without losing information. Okay, so now the question is, do we have information measures that can measure these different sources of uncertainty? For system variability, we have already seen we can use conditional entropy or unconditional entropy. But how do we measure uncertainty due to representativity, consistency, and compression issues? And there is a measure, or there are actually two measures with which we can capture this also in the unit of bit, and that's cross entropy and Kullback-Leibler divergence. And I'll try to explain that on the next slides. So this is also where, say, the modeling aspect comes into play, where we use models, compressions or representations of the data we learned from, and now apply it to new situations. So imagine the following case. You learned your optimal question tree from system A. Yeah, that was the one you were given, and you came up with this perfect optimal tree and this questioning scheme here. And now let's suppose you apply that to another dice that is, you go visit a family, they're rolling a dice, and you think, hey, I know what a dice works like, so I know the perfect question scheme. But unfortunately, this dice is not a fair one, but it follows this probability distribution that was system C a few slides before. And you remember the unconditional entropy of this was 1.75 bit. So if you had an optimal question tree learned from this system, you would on average ask 1.75 questions to identify the outcome, okay? Now you, unfortunately, start asking questions using this question tree. So you always keep asking, someone rolled the dice and you ask, is it smaller than 2.5? Yeah, and then the answer will be yes or no. And let's say it was yes, then you will ask, is it a 1? And so on. So you will always go down these branches of the question tree. And because these outcomes here are 1 to 4, and these are also in your question tree, you will eventually arrive at an answer. But you always ask 2 questions until you arrive at an answer. So even if the data generating system is this here, what you do is you ask 2 questions on average. So this means here the entropy of system C, you assuming it's a data generating system A, yeah, you using this question tree is 2-bit. So if you would play the guessing game, you would lose because you always need 2 questions on average, and others who learned from that system ask 1.75 questions. This is cross entropy. And this basically summarizes in an additive way the uncertainty that comes from your data generating system produces data with a certain distribution, plus the added questions that you need to ask because you're using a model, this question tree, instead of the true probability distribution and the true question tree. So cross entropy of X, assuming X hat, it's usually called an X hat. This suboptimal question tree could also come from the fact that you're using a limited sample of a system to learn from, yeah, and not the population, is calculated as the probability weighted information that is attached to each signal. And here comes the important thing. The probability or frequency with which a certain signal appears is the probability of the true data generating system. That's how often a 1, 2, 3, and 4 appears with that dice. But the questions you're asking come from your p hat, which is the number of questions here coming from your tree. Yeah, that's the difference. If you would learn from the same system, this would be p log p. So it would be simply entropy. But now, because these are not equal, you pay with extra questions. So cross entropy measures total uncertainty from data uncertainty and issues you're having because of representativity, consistency, and compression. So let's summarize that as model uncertainty. And now, of course, so that's one nice thing, because we measure various different causes of uncertainty with the exact same measure bit. In cross entropy, they're entangled. And you may ask the question, can we disentangle that? And you can. So what we see is, if we had learned the perfect question tree from system C, we said it takes 1.75 bits of questions. You paid now 2 bits, and the difference here is simply 0.25 bit. So, and that's Kullback-Leibler divergence, which is basically total uncertainty minus the data variability part of uncertainty. So that would mean that's the model-based component of uncertainty. So Kullback-Leibler divergence is simply cross entropy minus the unconditional entropy of your target. And so that's a nice thing, because you can then do analysis. What is the added uncertainty because the sample you learned from is only 10 or 100 or 1,000 and is not really representative of the true underlying population. Okay, so that's an aspect I like about information measures, because different sources of uncertainty that you would normally, let's say you work with, you measure data variability by variance, and you measure the error that is introduced due to your conceptual hydrological model that you're using with the Nash-Sutcliffe efficiency. You don't really have a good way to combine and compare these two components of uncertainty. And with this, you would have the possibility to. What will come as a problem is if you work in a deterministic paradigm, meaning your models always produce single-valued outputs, you will have to take assumptions and go at length to convert that to probability distributions, which you can then compare, say, to your crisp observation you want to compare your model prediction to. That does not mean that deterministic models, are correct. They just claim they perfectly know without uncertainty what the outcome would be. So that would be an argument towards using a probabilistic paradigm in modeling. Okay, now I'll move on a little faster, so we avoid running out of time. A few words about entropy limits. We have already talked about the lower and the upper bound. The lower bound is always 0 bit, and the upper bound would be that coming from a uniform distribution over the data, which would be log 2 of the number of bins or distinguishable states. And if we here take a look at this, look at entropy as a function of the number of bins by which you resolve, say, a value range, then you can see the upper limit here is this green line, which is simply this log function of the number of bins. The lower bound of a Dirac is always 0. And this here now, the pink is, sorry, the blue one is the distribution of soil moisture data of some sensor. And you can see if you resolve that distribution by more and more bins, the entropy also rises. But if you use these data with finite precision, say rounded, eventually this will stop. This will stop the minute by which each of these values lands in its own separate bin. That means each bin has a population of 1 and all the others have 0. If you now keep increasing the number of bins, because empty bins have 0 contribution to entropy, the entropy will simply remain the same forever. So you can then see that your entropy value will be limited by the number of data that you have and not by the number of bins that you have. So that's important to keep in mind. And so that also means if I simply tell you this distribution has an entropy of 10 bit, it doesn't really help you much if I don't tell you how many bins, by how many distinguishable values are resolved the data. What you can do to resolve this is then to state what's the entropy relative to the maximum entropy for that given number of bins. Yeah, so that puts an entropy value in a perspective that you can then use to compare among different distributions again. Okay, attached to this maximum entropy, there's also a principle for inference that was coined by Jaynes. That's the maximum entropy principle. And that simply states, if you put anything you know, all the constraints that you have on a problem, for anything else that you don't know anything about, you should express these unknowns by a maximum entropy distribution, meaning a uniform distribution. So that's basically a paradigm for inference that's a little different from our approaches, where we usually either ignore or assume as deterministic crisp value anything we don't know, that you should, on the contrary, express anything you don't know by a maximum entropy expression. I know Gray is a fan of the maximum entropy principle, and I read a great paper by Demetris Koutsoyannis, who used this maximum entropy principle to derive, for example, the ideal gas law or the Clausius-Clapeyron relation and others from very, very elementary physical constraints about, say, the volume a certain amount of water is contained in, the temperature of that, and basically are not much more than that, derived from first principles and the maximum entropy principle, these very fundamental laws. So that's really a very powerful paradigm for inference. Okay, so these were basically the most basic concepts and key terms of information theory I want to show today. And now we can use these to start thinking a little bit about what is independence, redundance, and synergy. And that basically enters the game when we have more than one predictor. So far, we looked at uni or bivariate distributions only. But what happens if we have two predictors, say temperature and precipitation, and we're interested in discharge, for example? So you remember mutual information for the bivariate case was done like this. So the mutual information between our discharge and rainfall is maybe that, and between discharge and temperature is this. But now what happens if we look at them together? Yeah, this can be illustrated by these two circles potentially having some overlap with each other and having overlap with our target variable of interest. Now, the visual representation of if these two predictor variables hold information about the target that the other predictor doesn't have would be that the two circles here overlap with the green, but they among each other do not overlap. In that case, the mutual information between x, the variable x, and the joint distribution of y1 and y2, that would be this area here, would be equal to the mutual information between x and y1 only and x and y2. Yeah, so these circles, the blue circle, overlap with the green. These would not overlap. Now let's suppose, because they are somehow, influenced by another superordinate variable, temperature and rainfall are somehow correlated, then it could be that they provide information about discharge, but some of that information is overlapping. Yeah, that's given by both of them. In that case, that would be redundancy, meaning that the mutual information between X and Y1, Y2 would be smaller than the two independent mutual informations. And that would be the case here, yeah, where these two regions overlap to some degree. The more they overlap, the more redundant they are in terms of what they know about the target. And the interesting case is then synergy. And that's at first a little hard to imagine. Synergy would appear if the mutual information between X and Y1, Y2 known together is higher than the two independent mutual informations. That means basically you only tap information about your target when you know the two predictors together. You could not learn it from one only and not from the other only if they play in a team. And I'll show you examples of how that works, because that's something I bent my head around for a long time, how that could be, because you cannot visualize it with these simple Venn diagrams. Okay, so here are some examples. Let's say our predictor data are Y1 and Y2, and our target is X, okay? Our outcome here has 4 distinguishable states, 1, 2, 3, and 4. And you can see each of these variables can take the states 1 and 2. If we now only look at Y1, you can see if it produces a 1, it points to a outcome 1. If it produces a 2, it points to a case 2. So these 1s and 2s are able to distinguish, to point to the outcomes 1 and 2. However, they don't do a good job to predict a 3 and a 4, because a 1 appears with a 3 and a 2 also appears with a 3. So they would not be predictive, would not contain any information about identifying a state 3 or 4. Yeah, it would not help to know predictor Y1. It's exactly the opposite for variable 2. This is not informative about distinguishing outcomes 1 and 2, but they will identify cases 3 and 4. So overall, because the cases where they are informative are not overlapping, yeah, so Y1 is helpful here, Y2 is helpful here. The pieces of information they provide about the target are independent, and you can see the mutual information of X given Y1 and Y2 is 1 bit, and that's exactly the sum of the two mutual informations of X and knowing one predictor variable only. So because here the equality holds, these provide independent information. Now let's simply assume the predictor Y2 is a copy, a one-to-one copy of predictor Y2. Yeah, so they look exactly the same. So here you can see the mutual information of X and Y1 is 0.31 bit of the other two, and the mutual information of X and Y1, Y2 known together is also obviously only 0.31 bit. So that means the sum of the two is much larger than this. That means here we have a severe case of redundant information. Yeah, one does not provide independent information from the other. Now let's look at a simple logical operation that would be the OR, the logical OR gate. That means anytime that one of these predictors or both show a 1, the outcome will be a 1. That's the OR gate. Now let's look at how much information in that case the predictors contain. Predictor 1 contains 0.3 bit of information about the target, the other also, but together the mutual information between X and knowing these together is 0.81 bit, and that's larger than the mutual information of the two added together. So this is a case where only knowing the two together helps you to identify the output. There's an even more obvious case, and that's the exclusive OR gate, where interestingly, each of the predictors taken separately is independent of the target. Yeah, so here y1, if it shows a 0, the outcome is a 1 or a 0, and if it shows a 1, it's also a 1 and a 0. So it has 0 information about the outcome, and it's the same case with y2. But if they then play in a team, we're unambiguously able to identify, to predict the output. Because if both show a 0, it's a 0. If they show a 0 and a 1, it's a 1. If it's a 1 and a 0, it's a 1, and a 1, 1 leads to a 0 again. So now suddenly, because they play in a team, they directly point to the outputs. So this is just an illustration of how synergy can happen. And the key thing that took me also a long time to comprehend is, in the same data set, a single predictor can have situations where it provides redundant information with another. In other occasions of the output, it can play synergistically with another predictor, and it can play cases where both are independent of each other. So these numbers here that we calculate are the net overall effect. So here we have a case of net synergy, but it does not mean that for particular situations, for particular outputs, they wouldn't be redundant or they would be independent. Yeah, so that's important. It does not mean there can be synergy only between predictors or redundancy only. It's just the net effect that is summarized here. Okay. And this kind of measures and analysis are often used in temporal settings, in dynamical systems, where you look at the synergy, redundancy, and independence of time-shifted signals to find out about cases of causality, or to use it as a hint for causality. And that's surely something that Rebecca and Jonas can talk about then on the workshop. Okay, and now comes one last part about modeling. And this also took me really a long time to wrap my head around. And maybe I can shorten the time for you to wrap your head around. So I label this conservation, dissipation, and innovation. And one key theorem in information theory is the data processing inequality. And that soberingly states, no processing of some variable y, deterministic or random, can increase the information that y contains about x. Yeah, if x is our target and y is the predictor. That means I can log transform my predictor data, I can multiply them with 100, I can do whatever I want with it. The information content of this functional transform of y about x will never be higher. Usually it will be smaller than the information content of the original variable y. Now, if you let that sink in for a minute, the question arises, why do we model at all? Because if you think of a typical conceptual model, you have you predict some output, and that usually predicts your key variable of interest. Yeah, so the overall output. This output here that we predict is a function, say here, of the interflow. Yeah, because that's upstream in the model. The interflow that we predict here is here in this simple model a function of the unsaturated zone reservoir, because that's an upstream influencing item in the model. Now, and the functional transform that we apply here is some linear reservoir equation or some threshold operation or something else, yeah, or an additive operation, and so on. So in the end, at the end of our, say, reversed model chain, we arrive at our inputs, our observations, for example, precipitation. So if all of these functional transforms of our data do not increase the information content of our forcing about what we're interested in, why don't we simply shortcut that, yeah, and just build data-based models using precipitation, predicting discharge? Because we don't add any information through these functional transformations on the way. That partly, by the way, explains why we are so successful with data-based models nowadays. But this then leaves the question, I mean, we think we know something informative that is encoded in the way we feed our input through a model to the output. And if the data processing inequality states, sorry, this does not help, why do we do that at all? And this has even another sobering aspect, which I want to illustrate with one example here. Let's suppose we use as our data transformation of the input the simple additive operation. Yeah, we simply add two numbers. And let's say each of these numbers is a random number which produces 100 distinguishable states. Yeah, so the numbers, the integers 1 to 100. So overall, we here have 100 by 100 paired inputs of U and V. And if this is a uniform distribution, then you can easily imagine the joint entropy of that joint distribution is log 2 of 10,000, and that's 13-bit, okay? So the information content or the variability of this input is quite informative. Yeah? It has 13-bit of information attached to it. Now let's feed that through the addition operation. The outcome of that will have a value range of 0 to 200. And the distribution of these outputs are this triangle. This is basically a very rough form of a Gaussian shape. And if you would add more than two numbers, this distribution here, due to the central limit theorem at work, would quickly resemble a Bell distribution. Yeah. So intermediate values are frequent because there are a larger number of value combinations that lead to intermediate values. Now, if we calculate the entropy of this outcome distribution that falls out of our data processing, then this is only 7.36-bit. That means from a rich variety of inputs with a variability of 13-bit, we now collapsed that to 7-bit of information only. And if you imagine that a lot of our operations in our models and also in nature are, say, of additive nature. And believe me, I tried all the elementary operations that MATLAB offers in these terms, and all of them are dissipative in the sense of that you will lose variability on the way. That means, say, in a provocative manner, are things, by feeding them through sequences of operations, are they getting ever more boring? Which would mean, is our universe getting more and more boring? And is what we can output from our models always less informative, less variable than what we put in? And this is clearly, counterintuitive. Because we think our models provide, and as the world evolves, it will provide a richer variability of things than, getting ever more boring. You could also phrase this question a different way and simply ask, how does a random number generator work? Because you basically put nothing, maybe except a random seed, into a random number generator, and then it produces information. So how is that possible? And the key here is memory and order. And I'll explain that in a minute, because so far we have talked basically about memory-less systems where you combine these two inputs to an output and you forget about the history, the chain of events that happened. So let's try that once more. For independent events, let's say this is our sequence of random draws of U and our sequence of random draws of V, and this is the outcome, the addition. So if you're interested in this, this will always be, and the distribution over these states will be more boring than the joint distribution of this here. But what usually happens in environmental systems is that we have time-ordered sequences of inputs, let's say rainfall and soil moisture, and we have systems with a memory. Let's say the current state, and that would be a typical Markov chain problem. The state of a system now is a function of its previous state, maybe of n previous states, and of the input that's coming in right now. And now you can imagine that a system, as it walks through times, it generates a history. And if you are then able to tap this history, you can start producing information from nothing, basically. Yeah, you can create a richer variety of states, of outputs, than things you put in. Here's a simple example. Let's say our system, again, consists of two inputs that are random numbers, random integers between 1 and 100. And now, instead of just adding them up, we add them to the previous state of our output variable. So x of t is u plus v plus x of t minus 1. This will be a very simple system. Yeah, it will add data on the way. So the interesting thing that happens here is that each time, each new state of the system will have never existed before, because you keep adding numbers. So now if you play that game for, say, 11,000 time steps, the distribution, the entropy of that distribution of outcomes here has already a higher entropy than the entropy of your data generating input. So memory does the trick here, and you can achieve states where the entropy of the output is higher than of the input if you allow for memory, or in other words, for recursion. And so this is also the case, by the way, in our conceptual models. Usually our state at time t of, say, the unsaturated zone reservoir is its own previous state plus some inputs. And that means here we can generate a variety of states. And this can be counterbalanced by this information destroying fact of, operations like addition and multiplication and threshold processes are effectively information destroying. So if you have a system that, let's say, a rainfall runoff transformation process, usually what you put in is much more variable than what you put out. Yeah, because our hydrological systems are usually low-pass filters that from a variety of things generate some boring output, an univariate time series. And this is because the essential effect of that is addition, accumulation, agglomeration. But you could have situations also where your system, because it stores a signal through time, through some memory terms, like, a linear reservoir, it can shift input signals over time. The simplest case is, of course, it rains in winter and then you have snowmelt in spring. And that means through tapping past sequences of data, you can then suddenly produce an output, a snowmelt afflicted discharge time series that has a higher entropy of what you put in. So it's basically this interplay of information destroying operations in your models and information generating memory and recursion processes. This is, by the way, of course, also the reason why people use neural networks to do modeling of dynamical systems and were not very successful. And the real success then came when you started using some kind of networks that used memory terms in them. Yeah, so memory is a key for innovation, basically. And this also then shows why random or how random number generators work. There are basically two different types of random number generators in this world. One is you tap physical systems. So you, for example, look at molecule positions in high temperature gases. So that would be a physically based random number generator. And the other class of random number generators are those that live from their own past. Yeah, so the linear congruential generator simply produces a random number by doing an operation of its own past. And you have to initialize that with a random seed. And from then on, it's a pseudo-random sequence. But because it operates in a very interesting way through the modulo with its own past, it can generate sequences that look like random. So they are basically innovators because they live on their own past. Okay. So that was all about, say, conservation, dissipation, and innovation. And this really has, you will see that in the work of Alec Boyd and Alexandra Jürgens, and this paper by Henry Lin. This has a very strong physical interpretation to it also. But now to conclude, I just want to show you very quickly some examples of how information measures can be used. This is one from work with a PhD student of mine here. We quantified the information content of weather radar data when we were interested in ground rainfall estimation. And so we were using different predictors. These are the lines in different colors here and different numbers of predictors. And we also evaluated what is the effect of limited sample size if our model, our predictive model, is simply the joint distribution of predictor and target that we learn from the data that we have. That's the simplest possible model you can think of. And what you measure here is entropy and cross entropy on the y-axis, and this here is sample size. And the black and the red line here, they are just there as a reference. The red line is the maximum entropy that you can achieve with the given number of bins we use for the target. So you cannot be more uncertain than this. And the black line here is simply the unconditional entropy of your target variable, ground rainfall. So that would be your uncertainty, your number of questions, if you guess ground rainfall simply by knowing the long-term distribution of ground rainfall. And now you can see here the learning curves, say, of different predictors predicting ground rainfall. Let's just look at one example here. The green line here uses radar rainfall measured at height to guess ground rainfall. And you can see if you learn this data relation from very few samples, you're pretty bad. Yeah, you're worse than if you would only work with the distribution of the ground rainfall. But you quickly learn, and in the end, if you have access to enough data, you're that much better than knowing only the target distribution. And you can also see that learning this kind of model already saturates if you are at whatever, a data size sample of about 1800. From then on, adding more data to the learning process is basically redundant. If you look at models that use higher numbers of predictors, for example, the yellow one uses not only radar rainfall, but also the month of the year as a predictor. You can see this takes much longer to learn, but in the end, it's also a bit better than the single predictor model. So this is just to give you a short flavor of that we can evaluate the goodness or the value of certain predictors, and how much their value depends on how many data we have at hand to learn the data relation. Another example here from the same work was we wanted to quantify the effect of deterministic compression. That's what we scientists usually do. We have a data cloud. Here, this dotty cloud here is the empirical relation between the radar reflectivity we measure at height and the ground rain rate we're interested in. Yep. So, and this is the quite, say, fuzzy relation between the two. What we usually do is we compress this empirical data relation by fitting some function to it. Yeah, for example, the red one. Yep. That would be an exponential function we fit to the data. That means we discard the true data relation and we claim that's the one, that's the essence of it. You can now consider this problem as exactly the same as before. We don't use the true question tree coming from the true relation between this and that, but we use a model thereof, which here happens to be a deterministic one. So the compression here is the operation that makes the true data relation a model of the true data relation. And although if someone gives you such a deterministic compression, you have the feeling, hey, we know exactly, if we know reflectivity, what rainfall will be. It's basically just a perceived certainty. It just hides the true uncertainty. And interestingly, you can quantify now with cross entropy the added uncertainty, because we're not using this fuzzy data relation, but the model thereof. This is the Marshall-Palmer relation. And this is now 5-bit, guessing ground rainfall based on the true data relation had an uncertainty of 1.6-bit. That means this deterministic compression increased our uncertainty. It increased the number of questions we need to ask to correctly guess the output, instead of what we would intuitively think, decreasing it. Yeah. So deterministic compression, unless it's warranted, because the relation really is a deterministic one, all the dots would plot on that line, adds uncertainty and does not reduce uncertainty. Okay, and another example that we will talk about at length on the workshop would be the information bottleneck principle, which, without going into too much detail due to time, is a principle for squeezing out of predictor data through an encoding all the information that is relevant about a variable, a target variable of interest. And by doing so, the information bottleneck principle suggests to do a trade-off, an optimization between two desirable quantities, maximizing the mutual information between your compressed input variable and the output. So you want to preserve as much in your compressed or transformed or encoded input about the output. So this should be large. On the other hand, you want to compress your input as much as possible. Yeah? You want to have a compact model of your input. So the mutual information between this and that should be minimized. And this together, this functional here, is this information bottleneck principle that, say, controlled by this multiplier here, balances keeping relevant information and making your model small. So this is an information formulated guideline, say, for compressing data into models that keep as much as possible about what you're interested in. So to quickly summarize, information theory for me provides measures for information content of data, of prior knowledge and models. and offers a quite general framework for system analysis and model building. And because you always work on probability transforms of your data, is discipline independent because you always work with units of bit, which can have also disadvantages at times, but that's, you map everything to the probability or information space, basically. Yeah, and this is just some more papers and textbooks that I can recommend. Recently, I discovered the literature by Nicolas Timme. I also recommended one of these papers for the workshop as prior reading, because I think he writes in a very, very accessible style. And that's about it.
Thank you, Uwe.
Yeah, you're welcome.
It's great, thanks.
Are you going to share the slides with us?
Yes,
for
absolutely.
like the literature, for example, at the end, and then also in general?
I'll put the slides up on the mural of the workshop, and I'll also put up the recording and put that somewhere.
Thank you. Much appreciated.
Yeah, you're welcome. So do you have questions and comments or additions?
So many. But first, there was one topic on the agenda that we didn't get to. I'm wondering if you could help refresh me on what it is. It was information, a measure of information content. I believe Hoshin's used it. I just wanted to make sure I read up on that before the meeting. Does that ring a bell?
So you mean it was mentioned in the outline of the talk, of the presentation today?
Yeah, I can touch base later about. I'll go back to the outline, and that's probably easiest.
Yeah, let's take a quick look. In the overview now, it said talk about the basics, limits, independence, redundancy, synergy, conservation, dissipation, innovation, yeah, and some applications. Something we didn't touch now at all here is algorithmic information theory. This is something that will play a role in the workshop and something that Hoshin is looking at a lot at the moment. I don't know if this is what you meant, Tim.
Well, it's okay. I can go back to the outline.
Okay.
I'll let others ask some questions, and then I'll have some questions.
I think I don't have much questions. I need to think about this. The only thing that came to my mind is maybe if you could give some feedback on like the limitations of information theory, and like in the terms of, I think I know that it's not always easy, right, to compute them from like actual data. Like it's a nice theoretical concept, but then in the practical applications, it's not always directly applicable. And if you could like maybe touch on this.
Yeah, so two things that I frequently encounter that make my life difficult are to estimate distributions from limited data and the uncertainty you buy from that. And there's a myriad of methods, say, to do either estimation of discrete probability distributions or of continuous probability distributions from data, and how to infill them if you don't have enough data with reasonable assumptions. And the second is what you lose when you work with distributions is if values are close to each other or not. Let's say your model in a probabilistic setting predicts your prediction falls into this bin or into that bin. For a calculation of entropy, it does not matter if it was off by 10 bins on a value range or by 1,000,000 or 1 bin. It just did not hit the bin. So the closeness of your prediction on a value scale does not count and gets lost. And sometimes, you know, being that close to your true value or that close can be a valuable piece of information when you use that in an objective function. Hey. So
interested in information theory.
I would have a question which is regarded, like related to that, I guess.
Mm-hmm.
And maybe it's stupid because it just came up to me, and maybe I should have thought about it more, but I guess I just ask it. So when you estimate the probability and then translate it to the entropy or information or whatever, is there like an asymmetry involved? Because if you're close to zero, information jumps a lot if you make an error there. If it's 0.001 and 0.0001, it's an extreme jump. But if you're close to 1, it's 0.99 or 0.999 or 0.999. It's a very, like the form of the logarithm is very flat there. And so the error is not penalized, I guess. So is this asymmetric?
So this is not at all a stupid question, but it's a very smart one. And the good thing is that there is the limit if you say calculate entropy as the sum of the probability of an event times the logarithm of the probability of that event. If it's a very rare event, the logarithm will go up to infinity, but the probability goes to 0. And in the limit, if you approach 0, the product goes to 0. So very rare events, although they are highly informative, don't contribute much to entropy. So in that sense, fortunately, it's not very sensitive, you know, if you have a probability of 0.01 or 0.11, 0.011.
But does this mean then it could be a problem for cross entropy if this doesn't exactly match, like if your one distribution thinks that rare events in the correct one are actually not that rare, and then this matching doesn't really work anymore, right?
Yeah, very, very good point. And it's rather the case that if your model assumes some event cannot happen, you know, it assigns a probability of strictly 0, maybe because it was not contained in your sample, but then reality tells you, yes, it does appear, then the Kullback-Leibler divergence and the cross entropy in that case will go to infinity, which means basically information theory punishes a model that was unable to predict an outcome that you observed infinitely. Yeah, and that can be good if you say, well, we should build robust models that can predict anything that can happen. And I want to immediately discard from a set of candidate models one that is too narrow in what it can predict. So this is where this problem of zeros and non-zeros becomes very dominant in the entire process. And what is typically done in such a case is you build a model, even if from your sample it says 0 for a certain bin or a certain value, a certain outcome, you assign a small but non-zero probability to this, saying, well, I didn't observe it, but from, say, physical considerations, I would not exclude it. And that's how you basically put a handle on that. And this issue, of course, does not happen, say, in models that predict values directly, like, you know, an LSTM predicting values from a series of multiplications of input values. Here, you can simply, you know, cover any value range that you want. Hoshin, you've raised your hand.
Yeah, I was just going to say that to me, the way I think about it is that information theory in its various forms, whether it's Shannon or algorithmic or representational, seems to be a robust theoretical framework for studying the kinds of problems that we're interested in. But you also have people, and so you have people working on developing the theory, but you also have implementational issues, which is true of any methodology. And so there's a whole group of people working on figuring out how to build robust implementations addressing the various kinds of things that you're talking about. So, for example, information theory has been used to understand machine learning. To calculate mutual information, high-dimensional spaces requires a very careful attention to how you calculate mutual information. Otherwise, you get bad, incorrect interpretations or results. So I think it's useful to think of it as a theoretical framework guides our thinking, and then when we apply it, we have to think very carefully about the robustness issues. I have to go to the door. I'll be right back.
One thing that comes at an advantage maybe is that you can combine, say, categorical predictors with numerical predictors easily because you map that to the probability domain. So, you can build predictive models that use as a predictor a color and a numerical value and whatever. And that really doesn't make a difference. And if you look at, say, typical objective functions that are nowadays used in, tree-based learning and classifiers and so on, more often than not, you will find that some entropy minimization or some mutual information maximization is the key objective function, or at least a choice next to some objective functions that use some, value distance minimization on a value scale.
I missed that, Uwe. You were talking about using information theory to put upper bounds on measures which are then used for actual optimization.
No, I was just saying that it doesn't matter if you use categorical or continuous variables in learning. If you map that to the probability domain, you can combine them nevertheless. Yeah, so that's all I have to offer for today.
For our machine learning colleagues, you showed that nice slide about information bottleneck at the end. If people want to explore how information theory is being used to understand machine learning, you can look up some videos by Tishby. I can't remember if it was on your list there or not, Uwe, but he's the guy whose group in Israel developed the information bottleneck principle and been using it as a guide to try to help them explain how machine learning works and why it does what it does.
And for example, how information is processed through different layers of a network, where at the beginning, say the states of neurons have high mutual information with the input still, and then eventually it turns and they will have high mutual information with the output in the end. And so this kind of analysis can help you to see whether your network is still over-constrained, say too small, or if there is a lot of redundancy in the sense that the different states of your model are highly redundant with each other. That would mean you can discard most of that. So if you, for example, want to weed out or sparse out networks, mutual information can be a measure to guide you there. That's, for example, also used in when you want to find out how the brain functions. You provide a stimulus, whatever, a light, and then you look at correlation patterns among neural activity in the brain to see which parts of the brain do what kind of information processing.
The other thing, just in preparation for the workshop, is everything that Uwe's been talking about is Shannon information-based concept, which is based on events that have a probability that you can associate a probability of occurrence to. But information theory is not limited only to events that can be described by probability distributions. It can also be related to events which are described as sequential operations or algorithms. And that's algorithmic information theory. And then there's a very tight relationship between these two that people have explored and can talk about at the workshop. But it's interesting because, so information is not purely a probabilistic notion. It's more generally an algorithmic notion, which of course relates to machine learning also, because machine learning is algorithms that processing.
Algorithms produce probability distribution. I don't know. Seems like you could go either way with that argument.
Sure. You got to read up on Solomonov. I mean, underlying it all is the notion of random events still. So even a Turing machine is driven by random events. But I was going to suggest him read in the recommended papers for the workshop is the two papers by Grunwald and on minimum description name. And I think you in particular would really enjoy reading those. I'm going through them right now because you have that's topic very close to your heart. So.
But they're dense. They're dense.
Yeah.
They're dense. But Tim's a statistician, so maybe.
Well, yeah, that might be overstating it, but right. I don't follow everything, but I think I'm grasping the big picture.
Well, I'm hoping we can help each other because, the first time I read it looked like this, and then after a while it starts to make sense.
Definitely. And I have a response to your statement about, you said changing units changes the information content. Is that right?
No, I was saying that's, I misspoke and Uwe corrected me. If you measure entropy as continuous entropy in a continuous space, which I'm not convinced is a good idea, then one of the drawbacks of that is that changing units changes the size of the entropy measure. But if you stay in discrete units, if you assume that you have a finite, it could be countably infinite, but as long as you have a countable number of finite states, then that problem doesn't arise.
Yeah, I think I can offer the missing piece to that. Maybe the call isn't the right time to do it, but it's sort of it starts with the proof by contradiction. Because I think that, what you're saying, let's see. Well, let me put it this way. Changing units does not change the probability of events, so it cannot change the information content.
That's correct.
Yeah.
It's the definition of an event. The problem is with the definition of an event. And in continuous probability, an event has zero probability. If you define it as being infinitesimally small on the real line. But if you define it as having a particular bin width, or it falls between this and that, then it actually has a finite probability. It's just a mathematical singularity issue.
And I guess
it used to bug us a lot, but we did figure it out eventually. Sorry, Jonas?
I guess the problem is in discretizing the continuous space in a way, right? Because I think purely in the formula, if you rescale your value space, then you compensate in the integral with the derivative of your transformation. So like on that level, it should be fine to rescale. I guess just when you discretize, something goes wrong, right?
Not in continuous space, because you have to think of continuity as the extreme limit of a set of discrete events.
Mm-hmm.
I mean, we don't ever measure anything in continuous space. We only measure something to a particular resolution.
I'm also still not understanding where the units of the measurement, that's what you're talking about, right? Come into this.
Okay. the entropy of a Gaussian distribution is 1.4189 plus log of sigma, which is the standard deviation of the distribution. That's just a form. Okay. Sorry, I'd have to derive it to prove it. In other words, the entropy.
Let's believe it for now.
The entropy of a Gaussian distribution is proportional to the log of the standard deviation. Okay. And if you have something which, if you measure x in units which has standard deviation of 1, then log of 1 is 0, and the entropy will be just 1.4189. If you scale it so that it now has units of half of what it had before, the standard deviation will be 2, and now it'll be log of 2. You know, in log 2 of 2 would be 1, and so now it would be 2 point.
But in the formula for the entropy, it just had the information and the probability. So then I suppose, like, I also think if you imagine discretizing it and you discretize it into twice as many states as you did previously, then I would understand that you've sort of scaled up the whole thing. But if you're actually doing it and taking an integral, then it shouldn't matter what the units are at all. You're still looking at a Gaussian distribution that has the same distribution of probability over whatever limits you're looking at. Or am I misunderstanding?
Just write it out mathematically and you'll see what happens. The reason why in discrete space it doesn't change anything is because the number of states doesn't change. Okay.
And what
if you've got 100 states, if you've got 100 states and
what is the number of states in this use case? That's
up to your choice. Let's say, you know, you have a set of data and you measure it in centimeters, and you discretize your space in centimeter bins, and you arrive at a certain distribution.
Are we only talking about discretizing continuous space, or are we talking about actually just treating it continuously?
This is a language problem.
Yeah. But so the only thing I wanted to say is, like, let's say we measure lengths of tables, me in centimeters and you in inches. And if we then discretize with the same width of interval, absolute width of interval, we will have exactly the same entropy of the distribution of our measurements, no matter if you measured in inches and me in centimeters, or, you know, if I convert my centimeter measurements to millimeters, that will not make a difference.
As long as you have the same number of unresolved states.
Right, okay, but we're still talking about, we're still using sums instead of integrals, and we're just summing over a different number of discretized states, and that's what we're talking about.
That's right.
Okay.
Yeah, it's just a peculiarity of
but when you say, like, when you say like the standard distribution has this, you didn't specify a number of bins, so I imagine you're actually talking about when you take an integral instead of binning it and then calculating it with a sum. And if you're actually taking an integral, then I don't see that there is a number of states, and it doesn't make sense to me.
There's a state density then.
There still have to do with discretizing it. So I'm not sure what I'm missing.
Go ahead, Uwe, you were saying it.
I was just saying then you have a state density, basically. You know, so
it's the difference between probability mass and probability density.
This will lead to very long and interesting discussions, the differences and the subtleties of continuous versus discrete entropy and information measures. And
if you dig into it, you'll notice that continuous entropy can go from negative infinity to plus infinity, whereas discrete entropy can only go from 0 to plus infinity. And it has to do with this difference in definition of probability, whether you're talking about probability mass or whether you're talking about probability density.
So beware of continuous entropy.
Be very aware.
I look forward to it. But yeah, right. This is, I think, to me, it seems like a central topic in going from theory to application is how you get around this. But yeah, I'm looking forward to the workshop. Thanks for organizing this.
Yep. You're welcome.
Except that the vast majority of the theory is done in discrete space. by talking about discrete numbers of symbols and events. So the coding theory, especially when you connect it to computer science.
Thank you.
Yes.
And I like, Hoshin once made that statement that continuity was just invented to, make a fundamentally discrete world better graspable and being able to put it into functions. But the core really is discrete and not continuous. Usually we think it's the other way around. We discretize because, we need to put a handle on continuity, but it's rather the opposite.
Well, if we were representing the true underlying discretization, then we would need many, many, many more bits than we usually use, I imagine.
Well, if you believe in Planck's constant, then the universe is resolvable only down to Planck's constant. Everything is discrete. But it's a philosophical issue, and it doesn't really get us anywhere. So.
And it's interesting that, all the things we do with computers essentially work on discretized finite states, just a number of digits you allow for numbers. So there's no even continuity. If we do whatever integration works in a computer is solved with a discrete approach, which I find quite interesting.
The alphabet example is a nice one, Uwe, because as you said, you have 26 letters of the alphabet, or 22, depending on which alphabet you use. And then you can combine them together to make essentially a countably large number, but approaching infinite number of words, right? So we can think of it as an infinite set of words, but it's actually a discrete countable set of words that you can actually make, depending on how many symbols you use. So Uwe and I think about 3 or 4 years ago, I finally came around to seeing it from Uwe's point of view, which is that everything makes a lot more sense if you are willing to think of the world as being a minimum description length simplification of what is really a countably infinite number of discrete states. And when we use functions and so on, we're just sort of simplifying things to make it easy for us to describe them, when in fact,
well, I think it's possible that a less simple representation in most fields might be theoretically impossible because the measurement error maybe of the state is limited to be larger than the difference between the discrete states in the underlying system.
Right. Yeah, we're always limited by our precision. An interesting question which we related to earlier was, is randomness fundamental or is determinism fundamental? And we don't actually have anything that we can actually describe as being actually random. Everything, to my knowledge, is the outcome of discrete algorithmic processes plus truncation, like the random number generator example. So we like to think of our world as being ultimately driven by random processes. But when you start digging down into it, you have to start questioning.
Good thing we have 3 days in September. Get some sleep before and...
Nice to meet you guys. And in September. Thanks a lot, Uwe.
Yeah.
Yeah, thank you.
Bye-bye. See you soon.
Bye.